Okay, so this is example 2 of your lesson today. I know these videos are a little bit longer and these problems are a little bit longer, but hopefully after these 2 videos it helps a little bit, and then you'll only have 2 or 3 questions on your assignment tonight. So I'll try to go through this video a little bit quicker. Obviously feel free to pause, rewind whenever you need to. So it says a farmer has a rectangular piece of land that is bounded on one side by a river. Okay, so got this rectangular piece of land. All right, let's just draw a rectangle and let's not close it. Okay, let's say that one side of this is a river. Okay. Okay. It says she would like to build a fenced enclosure around this piece of land to keep her livestock from straying. She will not need fence on the piece that is adjacent to the river. Okay, obviously, so you have some animals in here, and you're going to build fencing around these 3 pieces, but you don't need to build a fence around the river because the animals aren't going to go in the river anyway. Okay, it says the chain link fence costs $12 per foot, and the farmer has $3,600 to spend. Determine the dimensions of the enclosure so that the area is maximized. Okay, so this is opposite of the first example. Now we're not trying to maximize cost. We're trying to give these animals the largest bang for their buck, the largest area that they can wander around in for $3,600. Okay, so again, let's call this our X, and let's say these sides are our Y. Okay, I'm going to set up my 2 equations. I have a constraint. Okay, and this time it looks like we are constrained by cost, right? Because we only have $3,600 to spend. We're not trying to maximize cost or minimize cost. That is the money that we have, and we can't spend any more than that. Okay? And cost, remember we said in our last example, whenever we have cost, the extra step that you have to go through is what is cost related to? Okay, so let's look and see where else we have money in this problem. It says chain link fence costs $12 per foot. Okay, so this farmer must live in a different area because in our last example it was only $4 a foot, so she's getting ripped off. So if it costs $12 per foot, that means every foot that we put in fence, we're going to be spending $12, which is telling us that we're building a perimeter around this shape of fencing. So cost is going to be related to perimeter. Okay, and then we are trying to optimize. What are we trying to optimize? Maximize the area for the animals. Okay, and that area equation is going to be x times y is what we're trying to optimize. Okay, so let's set up our constraint equation. Right now we already set up our optimization. X times y is a. So to build this perimeter, we would have 2 times y, right? Because y and y is 2y. Plus x is equal to, actually, sorry, I missed something here. This is going to be $12. Sorry, I forgot to put in cost. $12 for each of my y's. And let me just erase this. Okay, and then I have, the money doesn't change, so it looks like it's $12 no matter what side we're on. So I'm going to say $12 for our x, and that's equal to what we're constrained by is $3,600. Okay, let me just take this one step further and simplify this. So this will be 24y plus 12x is equal to 3,600. Okay. All right, we have 2 equations. We have our constraint, we have our optimization equation. So what we always do with this is we take a variable from our constraint equation, manipulate it, solve for it, and put it back into our optimization equation. Okay, so I'm going to say y is equal to 3,600 minus 12x over 24. Okay, if I were to solve for y, that's what I would end up with. Okay, let's break this down a little bit further. So y is going to be equal to 3600 divided by 24 is 150. 12 divided by 24 is 1/2, and then we've got the x next to it. Okay, so now I can take this, plug it into my optimization equation. Okay, so I'm going to say x times 150 minus 1/2 x is equal to my area that I'm trying to optimize. Okay, let's distribute and simplify. So I'm going to say 150x minus 1/2 x squared is equal to area. Okay, we've got our area equation now. All we need to do is find our critical point here so we can get our x value. So the way to find our critical point, like we've always done in the past, is to take our derivative. So 150 minus, when I bring 2 times 1/2 is just 1, okay? X, 2 minus 1 is just 1, so it's raised to the first. And when I take the derivative of a, it's just going to give me 0. Okay, so this one's going to be pretty easy. So just bring the 150 to the other side, so it's negative x equals negative 150. I'm going to divide out my negatives, so I get x equals 150. Okay, let's make sure and double check that we are actually, this is actually the point at which the area is maximized and not minimized, right? We don't want to find an x value where the area is minimized. We want to find where it's maximized. So I'm going to say a double prime is equal to, let's see, this was a prime right here. So if I take double prime, 150 is going to go away, it just becomes 0. Negative x just becomes negative 1. Negative 1 is obviously less than 0. So if negative 1 is less than 0, that means we're concave down. That's our critical point. We're at a maximum, so that's good. 150 is our maximum, okay? To find our y value, I'd say y equals 150 minus 1/2 times 150. When you do that in your calculator, you get y is equal to 75, okay? I hope these examples help. Again, guys, please don't be afraid to reach out to me to ask questions. Your practice problems are next.